Hello everyone, welcome to yet another video of electromagnetic fields. So in this video series we are discussing about the concepts of electrostatics. So first we have discussed about Coulomb's law, and then we have discussed about what is electric flux and what is electric field intensity, and then we have discussed about electric field due to point charges and different charge distributions and all. In today's video, we are going to discuss about yet another law that governs electrostatics, which is Gauss law. So through this video, we are going to deeply understand about the fundamental principles of electromagnetisms with simplified calculations, and also we are going to discuss about what is Gauss law and how Gauss law is important in electrostatics and what are its applications. Now let's get into the video. So the agenda for today's discussion is, first we have going to look at an analogy to understand the Gauss law, and then we are moving on to the mathematical formulation of the law, and then how we can identify an ideal Gauss surface, and then with applications we are going to conclude the topic. So the key objectives is that we are going to understand the core principle of Gauss law. We already have Coulomb's law, but what is the need of Gauss law in this electrostatics? We are going to identify that, and also how electric field can be identified for different areas through this Gauss law. So this was the overall outcome and objective of this video. Now let's get into the topic. Before getting into the Gauss law, we'll need to understand what is meant by field pressure. So for that, imagine a balloon. The air pressure inside the balloon represents the electric field lines. Okay, so we are going to take an analogy of the balloon, wherein which the balloon is filled with air pressure, and the air pressure represents the electric field lines that are responsible, that are getting out from charge. So the charge emanates the flux lines, so that flux lines are being pressurized inside the balloon. When you inflate the balloon, the field lines or the air inside the balloon pushes outwards, which is perpendicular to the surface, right? So when you inflate it, the field lines will come out. The air will, with its pressure, comes out of the balloon, and that direction is perpendicular to the surface. Now consider the amount of air passing through any imaginary surface enclosing the balloon. So if we consider any air passing through any imaginary surface, we can understand that it is directly perpendicular, it is perpendicular to the surface, and the flow or the flux lines which are coming out from the surface will be related to the air inside. So how much of air inside the balloon, that will be coming out of the balloon, right, when you inflate it. Similarly, the electric flux line is a measure of the number of electric field lines passing through the given surface. So when you assume a surface, a Gaussian surface, you can clearly find the amount of electric field in that surface by clearly calculating the number of flux lines through it. So Gauss law states that the electric flux through any closed surface is directly proportional to the charges enclosed within that surface. So this analogy, it gives a detailed correlation between how the pressure of the electric field depends on the charges enclosed. So making this concept more abstract and tangible, so that we can easily make the students to understand how Gauss law can be related to a simple analogy. Now let's derive Gauss law mathematically. So as we already told, Gauss law states that the electric field intensity in a closed surface is directly proportional to the amount of charges enclosed. So therefore the closed integral over a surface S E dA, where E is the electric field intensity, over a surface dA will be equal to the amount of charge enclosed, Q enclosed. So which is given by the integration of E dA is equal to Q. So if we include permittivity, then it is Q by epsilon naught, and we can tell that as psi E. So this derivation begins by considering the electric field of the point charge, and which can be integrated so as to get the electric field for a whole surface. So the surface can be assumed based on the type of charge distributions, and it can be based on the different charges and the size of the particles. So now we are going to find the Gauss law. We are going to apply Gauss law to any surface or volume, for which we have to first assume a Gaussian surface, right? So now here we have listed a few Gaussian surfaces for different kind of charge distributions. If the charge distribution is a point charge, like which is the smallest interstitial charges, then for those we can assume spherical Gaussian surface, because the point charges ensures a constant electric field perpendicular to the surface. So for point charge distribution we can go for spherical Gaussian surface. If it is a line charge like in a filament or in a wire, we can take cylindrical, we can assume cylindrical Gaussian surface, because the electric field is radial and perpendicular to the curved surface and parallel to the end of the caps. So that is why for line charge distributions we can assume a cylindrical Gaussian surface. If it is a plane charge, that is the surface charge, then we can simply assume a cylindrical surface or a rectangular Gaussian surface, which is a pillbox surface. So through that rectangular box surface we can apply Gauss law. So because the field for that rectangular pillbox is perpendicular to the flat surface and parallel to the sides. So based on the charge distributions, we can choose the right Gaussian surface. But what is a Gaussian surface? It is an imaginary closed surface that simplifies the electric field calculations, because you need to find the Gaussian surface, Gaussian law. You can apply Gauss law, or if you want to find any field, first you need to assume a contour or a surface. You need to have an imaginary area inside which you can found the electric field. So that imaginary surface, closed surface, you assume is the Gaussian surface. Now how can we assume Gauss law? First we have to identify the Gaussian surface. Either it can be cylindrical or spherical, for which the radius is r and the length is L. Here we have mentioned for infinite line charge. First we are considering only the line charge. Here the symmetry is all the field lines points radially outwards. For flux calculations, the flux through the end caps is 0, since it is parallel to the area vector. So therefore E is equal to lambda by 2 pi epsilon naught r. If the charge distribution is a surface charge distribution or a plane charge, then if you apply Gauss law, you can get the formula for electric field intensity as E is equal to sigma by 2 epsilon naught. So for different Gauss surface, you can get a different electric field intensity formula by calculating the amount of electric flux density or field lines inside it. So because the field lines ensure the amount of charges inside, because Q is proportional to phi, which is the flux lines. So therefore E dA is equal to psi as per the Gauss law. So through this concept we have understand what is Gauss law and how we can assume Gaussian surface, and then what are the different Gauss law equations for line charge and surface charges. Now we'll have a quick quiz sessions where you could try to find the answers. Now first one, Gauss law states that the total electric flux through any dash surface is perpendicular to the total dash enclosed in it. We know that from the integration itself you can easily say that The integration is, you have a circle there, which means that the electric flux lines through any closed surface. That is why we are assuming a Gaussian surface here. So the first answer is it is closed surface and is proportional to the total electric field. Yes, field dense intensity, where E, because E represents the electric field intensity. Now what is the mathematical expression for Gauss law? It is integral, closed integral, E dot dA is equal to Q enclosed by epsilon naught. For point charge, the Gaussian law is E is equal to lambda 2 pi epsilon naught. For infinite line charge, it is E is equal to lambda by 2 epsilon naught. So through this equations, through this video, we have finally find out what is Gauss law and choose the appropriate Gaussian surface for each kind of distributions, and finally we have seen the practical applications. One thing I want to clarify here, we already have Coulomb's law, but what is the need for Gauss law here? We know that Coulomb's law, it gives the electric field intensity be 2 point charges, right? If you want to find for a whole volume or for a whole surface, then you have to apply superposition principles, so which is time consuming. But if you use Gauss law, it will yield the same result as like Coulomb's law, and also the method is fast by using Gauss law. So that is why we move on to Gauss law, in order to you can rapidly or easily find the electric field inside a larger volume. For Coulomb's law, it is time consuming. So therefore, in this video, we have so far discussed about what is Gauss law and what is the mathematical equation for Gauss law, and how we can assume Gaussian surface for different charge distribution and what are such applications. So through this video, we have discussed deeply about Gauss law and its importance. So we have unveiled the principle behind the electromagnetism through Gauss law. In the next video, we will discuss a different topic in electromagnetic fields. Thank you. Thanks for listening.